Third class, my name is Cadet Lachey. I'm accompanied by Cadet FICO, Cadet Peterson, and Cadet Whitaker, and we will be presenting our engineering design problem on our balsa wood bridge. For our problem statement, our group was tasked to build a balsa wood bridge that is capable of holding the given load. The bridge should be cost-effective, sustainable, aesthetically pleasing, reliable, long-lasting, and constructed on time. The bridge must also be able to withstand a load of 111 newtons.
So the constraints of the bridge, we were given it had to be less than 500 millimeters in length, less than 200 millimeters in width, and weigh a maximum of 100 grams. It must also be able to transport a miniature cat scraper through the middle of it. So the height minimum was 90 millimeters, and the minimum width was also 90 millimeters.
Now for initial design, we've chosen this road zipper, which has a length of 495 millimeters and a height of 100 millimeters. And in order to find this design, we had to determine the internal forces. So to do this, we applied a unit load at point J and calculated the forces inside each member. And we found that these two members at the top have the greatest internal compressive force, and these two at the bottom have the greatest internal tension force. Now to find which bridge we wanted to use, we had 4 designs, and we chose 3 qualities: weight, back external force, and aesthetics, to judge them based on. Of course, each of these qualities was given a rating, and each bridge was scored. And that weighting and score was used to give a total score for each bridge. And that is how we chose our design.
So for our preliminary design, we needed to calculate the cross-sectional area to form each member on the bridge itself. So in order to calculate the cross-sectional area, we used the applied force over the stress the bridge would experience. We used a factor of safety of 1.4 to calculate for any mishaps in our design of the bridge and in the building process. So during this calculation, we found that the minimum surface area for the greatest member in tension would be 29.27 millimeters squared, and also the greatest member in compression would be about 24.00 millimeters squared. So for the differences in our actual member design, we noticed that the 495 millimeters for the length stayed the same. However, the biggest difference was the members in tension. So we calculated the members in tension on each side and had the small beams on either side of the beam at the bottom. This was just to add a little more structure and a little more stability to our bridge.
Now obviously a few things we didn't account for in our design were the top here, which we decided to withstand compressive and tension forces. So we built some diagonals and some horizontal beams. And then also, while we were building it, we found that our designs weren't exactly foolproof and more difficult to build than possible, so leave a little wiggle room for the scraper to fit inside. We made it 110 millimeters in height instead of 100. And then we also made these beams on the side, which were in tension. We put 2 on each side to finish out.
May the forces be with you. Sir, class, this concludes our brief.